Okay. Good afternoon, and I'm quite sorry for the delay. Oh, okay. Typically, it's a Mac issue or HDMI. It depends. So good afternoon. My name is Laurent Bricteux, and I'm glad here to present you the work about numerical simulation of turbulent flow in recent turbo machinery configuration. In fact, this work was carried in the framework of the PhD thesis of Patrick Tenet-Edger, and this is his very last result, so it's fresh from the oven. And this is also the fruit of a collaboration with Yacine Béchan from the Korea in Rouen. It's a lab specialized in combustion and numerical simulation. And also my colleague Sergio Lavagnoli from the Von Karman Institute who take care of the experimental aspects of these kind of studies. Okay. So we'll talk about the objectives of the project I'm showing here. Some basic principle of jet propulsion, since I suspect not many of you have acquaintance with that, except some of the usual suspects in the room. Challenge in civil aircraft jet propulsion, what is a modern gear turbofan, then explain what is the relation with the spleen low pressure turbine cascade, the flow solver we use and the methodology that is associated to that, some results, and the conclusions and perspectives. So the objective of this project is to enable high-fidelity turbomachinery simulation at realistic operating conditions. And we want to extend the capacity of the Yales 2 code to address this kind of problem on tier 0 systems. We also want to validate the compressible part of the Yales 2 flow solver for turbomachinery flows in comparison with experimental data, which is quite important, and also to complement the experiment with time and space resolved three-dimensional flow prediction to better characterize new jet engine configurations. So as you may know, how an aircraft is flying, you have the weight of the aircraft, the mass times the gravity, the lift that compensates this, you have the drag, the aerodynamic drag that is compensated by the thrust of the engine, and we will define here what is the thrust. So imagine that you have a thrust producer like an aircraft engine. You have a velocity coming inside this aircraft engine at a velocity C0, so you have a stream of air at a velocity C0, and then the thrust producer expels gases at velocity CE. CE stands for ejection velocity. You can compute the thrust using the Newton law, so it's the mass flux rate times the ejection velocity minus the mass flux at the inlet times the inlet velocity. And you see from this very simple equation that when the pressure at the exhaust is adapted to the pressure of the ambience, so typically this term is cancelled, you can see that you have two ways to produce thrust. Either with a high mass flow rate, so a high m dot, a high number of kilograms per second that travels the engine, or a high jet velocity, a high value of CE. So these two philosophies are synthesized here. So you have here a propeller aircraft that moves a very large amount of air at a very low velocity, so meaning that the air is not accelerated that much across the propeller. Otherwise, you have a jet engine. So you may know these famous jet engines if we are paying it now. A jet engine that moves a small mass of gas at a high velocity. You see the inlet here, they are quite small, so it can only ingest a small amount of air each second. And in fact, this way of producing thrust is very inefficient. But since we are paying the fuel, it's not a problem. All right. What's inside a jet propulsion engine? Typically, that is a very simple configuration where you have a compressor that will compress the inlet air. Then when the air is at a very high pressure, typically 50 times that of the inlet, you enter this air into a combustion chamber that will raise the temperature to a very high temperature, typically 1500, 1600 degrees. And this gas now that is at a high pressure, at a high temperature, so having a very high enthalpy content, will expand through the turbine. And the job of this turbine is to drive the compressor. Then the gases are expelled at the exhausts and they are further accelerated in a convergent nozzle here. And so here you will have a high velocity jet, but as already mentioned, we will see that this is a quite inefficient way of producing thrust. You can make the same analogy with the typical 4-stroke cylinder engine. Now if we look at a modern aircraft engine architecture, it is quite different because we will split the incoming air flux. So typically you enter about 1,200 kilograms of air each second, meaning that if you have a building of 10 meter, 10 meter, 10 meter in the 3 dimension, each you are able to suck all the air in this building in only 1 second. So this is the job of this huge fan there, this huge ventilator that will draw a huge quantity of air each second. And you split this flow in a cold flow in blue and a red flow and a hot flow in red. So the hot flow is passing through the engine that I just showed you 2 minutes ago. And the cold flow is bypassed. And so the role of this big ventilator is to accelerate, but with a very few amount, the cold air, but a large amount of air. So the cold mass flow rate here is very huge compared to the hot mass flow rate. Typically, it's linked in what we call a bypass ratio, which is about 10. So you have 1 ton each second in the fan and about 100 kilograms per second in the core of the engine. So here the thrust is mainly obtained with high mass flow rate and low jet velocities, except for the red, but that's not the point here. And if we compute the efficiencies of a basic jet propulsor, a basic jet engine, you have the core thermal efficiency, meaning you compare the kinetic energy you provide to the air that comes into the engine to the fuel energy. So that's typical, the chemical energy content of the fuel. That is called the thermal core efficiency, and this one about 40 to 50%. Then you have the propulsive efficiency that will compare the thrust power, which is called the propulsive power, to the quantity of power that is transferred to the flow. So the same as here, the numerator. And you can recast this equation to show that it depends on the inlet velocity and the exhaust velocity. But as the exhaust velocity is here at the denominator, you want to have it lower to have a high propulsive efficiency. And nowadays, you reach 60–80% for the propulsive efficiency. And the global efficiency of the engine is the product of the thermal efficiency and the propulsive efficiency, which is called then the overall or the thermopropulsive efficiency. So typically, if you want a high thrust, you have a high mass flow rate, and if you want to fly efficiency, you have low jet velocities that will provide the best propulsive efficiency. And this will explain the trend of today to design new aircraft engine. So the thrust-specific fuel consumption is an image of the efficiency of the engine, or an image of the fuel that is burned, or also an image of the CO2 that is emitted. And you have 2 avenues there. You have first the propulsive efficiency avenue here. So either you try to increase the propulsive efficiency, or you try to increase the thermal efficiency. Increasing the propulsive efficiency means lower jet velocity, as we saw, more air for a given thrust, very large fan, this very large ventilator. Today it's more than 3 meters, the diameter of a fan, and very high bypass ratio that we just defined. if you want to go on the second avenue, so the thermal efficiency increase, you need to have high cycle pressure, meaning that you have to work very hard on the compressor. And today we already reach 93% efficiency for the compressor and pressure ratio over 50, so it's quite hard to make any incremental progress on that. High cycle temperature, meaning turbine inlet temperature higher than 1500 or 1600 degrees, meaning that it is a really high thermal challenge because you work very well above the melting point of the turbine blade temperature, and also better component aerodynamics, but we are already very high there. So this avenue is not easy at all. We made a lot of progress in the 30 last years, and the new progress there are only marginals. So the best avenue is to go to the propulsive efficiency way, and this is the trend today, is to leading towards engine with a larger fan diameter. And today, the state-of-the-art of modern aircraft engine have thermal efficiencies of about 40–50% and propulsive efficiency of 70–80%. And the aim is to go on higher propulsive efficiencies. And for that, people designed what is called a gear turbofan. And in fact, it's a quite complex machine because in a modern aircraft engine, the fan, so this huge ventilator there, is driven by the turbine at the back of the engine, which is called the low pressure turbine because it's located at the end of the expansion of the gases. And so you have a close link between the fan performance and the low pressure turbine performance. The fan produces 80% of the thrust. So the low pressure turbine that drives this fan is a major component in an aircraft engine. So the LPT is a major component for the design of high efficiency gear turbofan. The problem is that this fan, as I already mentioned, is more than 3 meters diameter. So it wants to rotate very slowly, the slowest possible, to avoid centrifugal forces, tip blade shock and compressible flow issues, and to make low noise. While the turbine that is connected and that is driving this fan wants to rotate very high, at a very high velocity, because it's composed of airfoils, and as you may know from aerodynamics, if you have a high speed, the airfoils lift more, and so it's more efficient for the turbine here to rotate at a high speed. So you have a kind of problem there because this one wants to rotate slower, and this one wants to rotate at a fast velocity, at a high velocity. And so the idea is to put a gearbox between the low pressure turbine and the fan so that they can rotate at the optimal speed. The problem with that is that it will lead to new flow regime in the low pressure turbine that we don't know and that are not explored yet. So the LPT operate in flow regime that favor boundary layer separation and also profile losses, and that's what we will present as results today. So that's an image of the gearbox. And if we talk about the gearbox, you see here the power of a classical ODI5 that is well known from some people of the assembly here, which is about 300 horsepower. And the power in a gear turbofan, so the power transiting by this gearbox, it's about 50 megawatts. So 226 times the power of an ODI5. So this gearbox has to transfer more than 200 times the power of an advanced car gearbox. And it poses also some challenges in terms of lubrication, so to limit the frictional losses, the heat generation, the load bearing, but also in terms of material strength and durability, in terms of weight, since we are working with an aircraft engine, so the weight is the first enemy, and in terms of engine integration for thermal management, noise, and maintenance. If you want to talk about the number of teeth here on the gear of the main shaft, you have about 34 teeth, and these 34 Ts has to transmit a power of 50 megawatt. So it's quite huge for one T. So you have to take care here, as depicted in the picture, of all of these Ts. So the challenge now for the low pressure turbine. So let's remember that the low pressure turbine is a turbine located at the back of the engine. We know that the geared engine architecture allows to decouple the fan and the turbine shaft so that they rotate efficiently at their own speed. It will lead to moderate Reynolds number flow and transonic speed, meaning speed at quite elevated high number compared to classical turbomachinery application. And this impacts the boundary layer flow, the boundary layer flows and the compressible effect with the shocks, and also thus the aerodynamic performance of the component. And there is a gap in research and industry for this new design space. Also a lack of accessible experimental data to provide useful boundary conditions for CFD codes. And for that, there was a European project called Clean Sky, in which the Von Karman Institute and Safran Aircraft Engine teamed together to provide the scientific community an open source database of an open source low pressure turbine blade with experimental results so that CFD guys can validate their code. And this is the aim here, to validate the compressible yields 2 flow solver with quantitative comparison with experimental data. So they made a lot of tests in their transonic compressor wind tunnel. You see here that you have the blade cascade. So typically they put the low pressure turbine blade in a cascade. And here something important, they have a grid here. And this grid, this array of rods, is intended to generate suitable turbulence. So we will talk about that also later. We will use here the yields 2 flow solver, which is not an open source solver, but this is a solver that is developed at Coria in Rouen, and about 200 people are working on that in different laboratories. For instance, in Mons, we are working on it, in ULB, in Université Catholique de Louvain also, sorry. We are working on the yields 2 flow solver, but the core team development is Vincent Mouron, Guy Lartigue, and Pierre Bénard. It can handle structured and unstructured mesh, so you can deal with very complex geometries and use adaptive grid refinement. It solves the 3D Navier-Stokes equation in different regimes. It uses a double domain decomposition to exploit the cache quite efficiently. And you also have highly efficient linear solvers. It's a classical, it's a 4th order central finite volume method and a 4th order time integration, and it's suited for massively parallel computing. Here you see some application. So it's an aeronautic burner. Here it's a lubrication problem of a disk that rotates in oil. This is the suction side of a high pressure turbine, and this is a moving mesh with a simulation of the human heart. So we tried to install it on LUMI with some success. We did the scalability performance, and we see that we still have a good scalability up to 8,000 cores. To be honest, for the moment, we experiment some issue with the METIS partitioner, the domain partitioner METIS, that alter the scalability. And since I just here in the previous presentation that we can ask for support, I will try to fix this problem with these guys. Well, and we are solving with yields 2 the Navier-Stokes equation for compressible flow. I will not enter into the details, so that's typically the mass conservation, the momentum conservation, and the energy conservation. And in the momentum conservation, we had a fourth term that is intended to model the turbulence grid generator. So this is the shape of this front end, and you see that you have a lift force, a drag force, and in fact that this lift and drag force will depend on time. So that it's called a dynamic actuator line method, and that is intended to reproduce the turbulent grid generator of a wind tunnel. So it introduced temporal fluctuation and CL and CD coefficient. To show you that in a simpler picture, this is the cascade that reproduces the cascade in the wind tunnel, and this row here of forces represents the rods that I just showed you from the experiment. And you see that the flow is incoming like that, and the rods leave a wake, and these wakes are mixed, and they generate homogeneous turbulence in upstream of the test section. So the dynamic actuator line method allows to reproduce the same von Karman wind tunnel turbulence condition. And we worked quite hard to have the correct level of intensity in the reference plane and also the correct length for the turbulence structures. So talking about the computational domain and the GMesh mesh, so we use the open source software GMesh to make the mesh. And you see that this is a structured mesh in the region of the boundary layer, so close to the wall, where the velocity varies quite heavily. You have a very, very fine structured mesh. And outside of this region, you have a non-structured mesh. You also refine, but it's not quite clear here, I'm sorry about that. In the wake region, you also refine the grid. And we also mesh the inlet of the wind tunnel, and we locate the turbulent grid, the turbulence grid bar generation here at the correct location with regard to what is in the reality. That's the shape of the blade that is provided by the Splint project as an open source blade, which is not a trivial question because usually aircraft engine manufacturers don't share their secrets. Typically, the shape of a blade is an industrial secret that is kept very secret. So here they make an open source, and this is quite original. About computational time, when we launch this kind of simulation around turbine blade, we have what we call a spin-up time, meaning this is the time needed for the statistical convergence to be achieved. So you see that here at the beginning you have a huge transient, and then after statistics are converged around a mean. Okay? It doesn't mean that the flow is steady, it means that the statistics become steady. And when you reach a time of about 43 here, you dump all in the trash and you begin to collect the new statistics. So you remove all the transients part of your computation and you gather the statistics. Typically, it was 384 wall clock hour and about 300 hours for the statistic gathering. 10 convective times on LUMI using 768 cohorts takes 86 hour wall clock. So the computational cost for one complete run is about 500,000 CPU hours. So now I will show some movies, and what do you have to observe in this movie? So this is typically the blade cascade. So we reproduce the blade cascade of the von Karman Institute. So you see that the blades are not located like in a real aircraft engine on a circular ring. They are disposed linearly in a cascade. And what we see here is the vorticity, the vertical structure. You see here the boundary layer in red. This boundary layer is subjected to instabilities. These instabilities grow, and then here at the trailing edge, you have a shear layer and you have vortex shading with three-dimensional structure. Since we are dealing with compressible flow, you have acoustic waves. Here you can see the compressibility effect, and you also have shock waves. And these shock waves can impinge on the next blade boundary layer, leading also to what is called a shock wave boundary layer interaction. So the shock wave can perturb here the boundary layer, make it separate, and then degrade the aerodynamic performances. You also have turbulent structure on the pressure side. So this is, for those who don't know, the pressure side, and on the top, the suction side, like an airfoil of an aircraft. And you also have a boundary layer separation on the pressure side. So it is typically what is observed when you have a clean inflow. So we don't put the turbulence bars at the inlet. You see that you don't have any turbulence in the flow passage. You see the shock waves here impinging on the next blade boundary layer. You see long elongated vertical structure. You see here the vertical street in the wake, and you have on top of that the 2D clearance of the density variation that also shows the shock waves and the acoustic effects. Now, if we put the turbulence grid, so let's recall that here we emulate these row of cylindrical bars, but we don't mesh them, we just replace them by a source term, a force source term in the Navier-Stokes equation. And in fact, it is a convenient method to inject turbulence. So you see here it's quite slow with regard to the reality. Of course, the movie was slowed down. And you see here the turbulent vertical structure that are generated in the wake of the bars, the homogenization of the turbulence, and here you are at the right level of turbulence just in front of the cascade with the correct length and the correct turbulence intensity. You can already see that the wake here is much less coherent than in the clean inflow case. So the wake vertical structure exhibits reduced coherence due to the interaction with the turbulent structure. So you see that here in the passage channel you have some turbulent structure. And this effect is more pronounced at lower Mach number. So here we are considering Mach is equal to 0.7. Now, if we compare the different Mach number and the fact that we use a clean inflow or a turbulent inflow, we can see that in the low Mach regime, 0.7, 0.8, 0.90, the boundary layer separates on the suction side on the 3 cases, while at a higher Mach number, 0.95, it stays attached in this region on the aft part of the suction side. You see that the boundary layers are attached even if you have turbulence. You see that here you also have the shock wave, and here you only have some acoustic effects that are negligible in the low Mach regime. You see also that the turbulence is, in this case, entering into the channel, while here the channel between the two blades are clean. So the inlet turbulence accelerates the development of turbulent structure on both sides of the blade, and it also modifies the shear layer dynamic and weakens the vortex shading coherence. You see here that the vortex street that emanates from the trailing edge is much more coherent than what we have here when we inject the turbulent inflow, when we take into account the correct turbulent inflow of the wind tunnel. Now we could talk about quantitative diagnostic. So this is the Mach number distribution on the suction side and the pressure side of the blade. And so it's an image, in fact, of the velocity distribution on the blade. So on the pressure side, the flow accelerates. On the suction side, it accelerates. It reaches a maximum and then it decelerates there. And this is the dangerous region. It's the aft part of the suction part. And this is where the boundary layer or the flow is subject to a separation. So the black square are the experimental points, and you see that the present work here, the LES in red, reproduce quite well the experiments. And on top of that, we see here that in the pressure side region where the boundary layers separate, you see that when you use the correct turbulence at the inlet, you are able to fit the experimental result much more closely than when you use a clean inflow. So this highlights you the role of the turbulent inlet and the importance of modeling properly the turbulence inlet. And as already said during the introduction of the talk, the aim of the CFD is to make it possible to extract quantitative information in flow region where experimental access is limited. Here we have an experiment that was carried between ULB and von Karman Institute. It's an optical measurement that is called particle image velocimetry. And you see that close to the walls, you have no good prediction. And the window, the optical window where you can make movie and average the image is quite limited. While in the numerical simulation, you can, for instance, access at the levels of turbulence in the region where the boundary layers separate on the pressure side. So if you can say that if it is okay here in the wake if you have the same number compared to the experiment, but in the experiment you are not able to go there and measure what happens there, then the numerical simulation helps you because there you have access to this information thanks to the numerical simulation. Another important quantity is quantifies the aerodynamic performance of the blading. So I will not enter into the detail here, but when we were talking about aerodynamic performances of the components, it can be lumped into numerical diagnosis. Then you can assess from the numerical simulation. And again, here you see that when you take into account the correct turbulence at the inlet of the blade cascade, you are able, for instance, to predict correctly the peak of loss level when the turbulence is properly modeled. And so, as conclusion, what we will do next and what have we done? We have shown here that the DLM enables, so dynamic actuator line method enables realistic inflow turbulence that allows to better match the experiment that were carried at the von Karman Institute. The turbulence injection improved then the blade loading and the separation prediction. It has a strong impact on the transition and reattachment at low Mach number. And the shock-driven physics dominate at highest Mach number, and the wake losses are better predicted with realistic inflow. So that's all the conclusion of the study we carried there. And the perspective are simulating now not static bars, but passing bars that emulate the stator vanes that are in front of the rotor vane with moving dynamic actuator line methods to also simulate the 3D effect, because we consider a cascade. But now, if we consider the end walls of the turbine, you will have a lot of different vortices that will interact with the main flow and that will alter the efficiency of the turbine. So it's also quite interesting to simulate this. And also simulates technological effects like purge flow that allows to prevent the very hot flow of the turbine to enter inside the mechanisms that are located inside the turbine disk. Thank you for your attention.